Good afternoon, everybody. It is my absolute honor and pleasure to invite our distinguished speaker for today, Professor Donald Sadoway. Let me say a few things about him before we start. It's a journey that I've followed since many years, and I'm so delighted that I wrote him an email as the first, speaker for the REINVENTS Distinguished Lecture. He accepted, but someone I've followed over the last 20 years, at least, of my life and learned a lot from. So let me start by saying that Professor Donald R. Sadoway is a professor of materials chemistry, emeritus in the Department of Materials Science and Engineering at Massachusetts Institute of Technology. His degrees, his bachelor's and his PhD was in chemical metallurgy. And he got this from University of Toronto. He's authored over 180 papers, published over 40 patents, and one of his most significant achievements has been to take scientific discoveries, the first principles, to translation. And specifically in the area of energy storage, he's really developed so many technologies that have done amazingly well. For example, some of his accomplishments include this very famous, the liquid metal battery for large-scale stationary storage. He invented the process of molten oxide electrolysis for carbon-free metal production. He's a co-founder of 6 companies such as Ambry, Boston Metal, Luna Resources, Avanti, Battery, Pure Lithium, and also now most recently Sadoway Labs. One of the first things that I actually came to know Professor Sadoway was through his online lectures at MIT. He did a course on solid-state chemistry. I used to absolutely hate chemistry, and I started looking for resources, and he had this course on solid-state chemistry, which I really recommend everyone to see. The course not just covers fundamental chemistry and crystallography and solid-state concepts, but it also he blends in literature and music and Michael Jackson in these videos, and so it makes it a completely unforgettable experience. And that's where I kind of really was first introduced to Professor Sadoway. He's also given TED Talks, which have been viewed about 2.5 million times, which I'm not surprised about at all. And he's spoken a lot about inventing technology. He's won numerous awards, and I will specifically allude to one of them. He got the award for the best engineering communications from Department of Energy. He's also been on Time magazine as one of the 100 most influential people in the world, and his achievements have far-reaching consequences. So please join me in welcoming Professor Sadoway. Thank you. We are delighted to have you here, and I really look forward to look forward to hearing about your work on electrochemical pathways towards deep decarbonization and profitable sustainability. Thank you.
Okay, so when I got the invitation to come here, of course I couldn't say no, because it was here that in 1962 that President Kennedy rolled out his announcement that he had an intention by the end of the decade to put a man on the moon. And I think it's salutary that that was done not at MIT, never mind that NASA was going to be in East Cambridge at the time, not at Harvard, not at Stanford. It was done here at Rice University. And that means a lot. And so when I saw that invitation, I said, there's only one answer. It's hell yes, coming here. So thank you very much for the invitation. So today I'm going to talk a little bit about this topic that's up on the screen. And so just to clear the throat, I have to say a few general things. So I've been looking at the reInvents website, and it's clear that you're interested in energy transition, stationary storage, and so on. So I think we can agree that a sustainable future is going to include a low-carbon electric future. You notice I said low-carbon. I didn't see carbon-free. I know I'm in Texas. I'm not going to say there's no hydrocarbons. I don't believe that anyways. I don't believe net zero. Don't believe that. And we're gonna learn how to accommodate. We're not gonna just declare that I'm gonna stop burning, and I'll show you how to get around it. And so that's gonna mean a lot of electrification. And electrification is not trivial. It's gonna require resources that we don't necessarily have. And that's going to get into topics that are unpleasant for most people, mining and smelting. I mean, this is not sexy stuff. When I started, I've always worked in this area. And people would kind of look at me askance saying, what's he doing this for? When they were closing out all the metallurgy departments in the country. It was metallurgy becoming material science was getting into nano, all kinds of tiny tech and blah, 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 blah. And then by the time we got the awareness that we have to do something about climate change mitigation and so on, where are all the metallurgists? Well, you exterminated them. You lost the thread, except I hung on. So I'm the last of the, yeah. And this is not trivial because you're talking, when you talk about mining and smelting, you're talking about some of the most conservative, risk-averse sectors in the economy. They hate uncertainty. Just as the automobile industry hates uncertainty. That's why they foot dragged on switching to electrics, because they're experts. They got 100 years advances, head start with the internal combustion. Now that that's all thrown away, they have no advantage. Some upstart can come out of nowhere with an electric buckboard with a joystick, and this really irritates them. We have to reinvent all of this stuff. And in the 21st century, the regulations on emissions to air, to water, to soil are so stringent. I mean, to try to get permitted in the United States, to even get a mine, let alone a smelter, I mean, this is going to be so difficult, which means that the challenge is that much higher. No problem, sign me up. President Kennedy says we choose to go to the moon not because it is easy, but because it is hard. And that's why I choose to work in this sector. The easy stuff is coding. I don't care about that stuff. This is real stuff. So, and by the way, all of this stuff falls into the domain of what we call tough tech. Tough tech is heavy industry. It's not sexy, but it's really hard too. It's not like writing code. We're talking 20-year time frame from the time of conceptualization to reduction of practice to start the company to commercial deployment. It's 20 years. Well, for you young people here, you say, that's cool. But for some of us, we start thinking 20. That's a long commitment. All right, so what I'm going to do with that as backdrop, I'm going to give you two vignettes today, and in the vignettes, I'm going to talk about both the inventions, and I want to give you some glimpse into my thought process, because I'm always a teacher. I can't resist teaching. People, there's seats up here. Come on, business class seating right here, front row. No questions. I won't put you on a spot. Come on up here. There's more over here too. Come on up. So I'm going to show you the thought process, how I got to this. So the first one is decarbonization of manufacturing. So that's green steel, and that led to the formation. Please come, Boston Metal. And then the second one is was alluded to, treating the intermittency of renewables. So that's stationary storage, and that led to liquid metal battery, which led to the formation of Ambri. So let's start about steel first. The 2024 figures haven't been published, but they're pretty much the same. So in 2023, 1.892 billion tons of steel. And that's virgin metal. Forget all the stuff about recycling and electric arc furnace. It doesn't count, right? We're talking 1.8 billion tons of virgin metal, dirt to metal. And that generated about 3.6 gigatons of CO2. And that represented almost 10% of total CO2 in 2023. That's not 10% of the CO2 that came from the manufacturing sector. That's 10% of world CO2. So to give you a sense of perspective, if I took all the steel companies in the world, lumped them together and labeled them as a country, it would be the third largest polluting country in the world. Number one is People's Republic of China. Number two is the United States of America. And number three would be Republic of Steel. That's how big this thing is. That's why I go after it. You know, why go after little? Somebody says, have you ever thought about greening the production of silicon? No, because who cares? Amount of silicon is produced, amount of CO2, you can't even find it. It's in the error bars. This is where you go. They had this guy, Willie Sutton. He was a bank robber, and he was arrested and imprisoned many times. And every time he was let out of prison, he'd go and rob another bank, and he'd get caught and go to prison again. So finally they said, oh, Willie, why do you rob banks? He says, because that's where the money is. So that's why you work on steel, because that's where the CO2 is sourced. So now the thought process. So I got to invent beyond the blast furnace, because steel is made in the blast furnace. That's where you feed in iron ore, you feed in coke, you feed in some limestone, and out the bottom comes liquid metal. And out the top comes CO2. All right, so first of all, I taught the big freshman chemistry class, so I know iron is found in nature as the oxide, either Fe2O3, iron 3+, hematite, or magnetite, which is a double oxide. It's FeO and Fe2O3. There's always iron oxide. And I know that the electron can be a reducing agent, sustainable, meaning that it can be produced without burning carbon. So if I put those two ideas together, I think I have something. And why is the electron a reducing agent? Well, when you think about what goes on in the blast furnace, what's going on in the blast furnace? You put in iron oxide, let's say Fe2O3, so iron is Fe3+, and it comes out the bottom as Fe neutral metal. Somewhere inside that blast furnace, which is not an electrochemical device, it acquired 3 electrons. Where did it get the electrons? Got them from the carbon. The carbon has this job of being the electrophore. It delivers the electrons. That's what it's doing. And also the combustion gives off heat, so it drives the chemistry at elevated temperature. So instead, get rid of the carbon and just deliver the electrons directly through an electrode. That was the way I thought of it. So if you put those two ideas, plus I have to make a soup. I have to dissolve the oxide in something, and I knew from teaching chemistry like dissolves like. So if I have a solid oxide, I'm going to make a molten oxide, and that's going to be above the melting point of iron because I want to make liquid metal. So we're talking about, 1,600 degrees centigrade. I don't care what the difference does it make? It's just the temperature. We're going to make it and go that way. So that was how we started, and that gave us molten oxide electrolysis. Solid oxide dissolves in molten oxide. Electron is delivered through electrodes. That's electrolysis. That's the thought process that gave us molten oxide electrolysis. Everybody said it was crazy because the electron is too precious, a reducing agent, and so on. And I said, yeah, but this is like 1986 or something like that. I said, don't worry. At the price, we'll figure out how to make that work. And so this would be disruption if we get this thing to work, because it's just like aluminum manufacturing, only at much higher temperature. So this is the schematic of the cell. If you look here, you see the molten oxide, this orange zone here. So that's the molten oxide solvent. And then you break the crust and you introduce oxide. And by the action of electric current, the current passes between the two electrodes. So you've got the anode up here at the top and the cathode down here at the bottom. The action of electric current, it does two things. It keeps the cell at temperature because it generates heat across the electrolyte, and it drives the electrochemical processes on both electrodes. So here we've dissolved the iron oxide, and then by the action of electric current, we make liquid iron at the bottom, and we make oxygen gas at the top. No carbon emissions. All right, and this is much cheaper than a blast furnace. Much cheaper than a blast furnace. Because a blast furnace, to get the iron oxide in there, first you have to pelletize it in pellets of a certain dimension. I know a lot of chemical engineers in here, so you got to figure out what the particle size is, what the porosity has to be, what the residence time is as it falls down, and so on. And we don't need coke ovens, because coke ovens start with coal, and they sinter it, and they kind of make it puffy and reactive. Again, for the chemical engineers, figure out that one. And you need the sintering plant to make the pellets. And then at the end, you end up with You start with iron oxide, you react with carbon, you get iron, but it's got too much carbon in it. So you switch the oxygen for carbon. It's got way too much carbon. So now you go to the basic oxygen furnace, and with a lance, you blow oxygen through molten iron to get the carbon out. Every one of these things costs money, capital cost, operating cost, and so on. We don't need any of that. And we could run this thing at 100,000 tons per year. Blast furnace would be minimum 2 million tons per year. It doesn't scale. So that's why you don't see people opening up integrated steelworks. You see them closing integrated steelworks. So this is the beginning. It's in the basement of Building 4 at MIT. So this is a cell. At the top here, you can see this is an alumina tube, and up here it's feed-throughs and blah, blah, blah. And down here, below the field of view, is the molybdenum disilicide windings, and this thing is running at some elevated temperature. What is it, 1600 degrees Celsius. It's blinding white heat, and why you see the light's being conducted by the aluminum oxide. It's at some level, it's beautiful, I guess, if you can appreciate beauty of this nature. All right, so we had a port on the top, and now we're going to look down, and we're going to see the current passing. Oh, by the way, I was funded for a while by NASA to make oxygen on the moon by molten regolith electrolysis. So we did this, so because it was NASA, we could use platinum group metals for the anode. So platinum group metals are serving as the anode. That's over here. This is the plus electrode here. This is the anode. You're going to see oxygen bubbles, and this is a molten regolith simulant. They wouldn't give me real moon, but they gave me stuff from Arizona, a meteor crater. So I have a simulant. And then on the other side, we have a tantalum plate, and then the liquid metal is dropping to the bottom. And so you can see it's viscous, but it's still fluid enough to allow the oxygen to evolve here on the anode. So this is an evolution of oxygen. All right. So we did not only iron. So you can see this is some iron that's stuck. You have to believe me, I didn't use epoxy to make this. We also did nickel from nickel oxide, trivial. And we wanted to do chromium, but chromium melts at 1900 degrees Celsius, which is higher than our furnaces could go, not because we were afraid to go to 1900. And so we made ferrochromium. So we electrolyzed chromium oxide into liquid iron and made ferrochromium. So this thing works. And then we could go above 1700, just a little bit, so I did titanium. So this is in one step, we took titanium oxide directly to liquid titanium. So we just went all over the periodic table and did the molten oxide electrolysis. But as I said, no one's going to build a steelworks with platinum group metal electrodes. That's impractical. So we needed to discover a practical inert anode, and that's what we did. And so with people around 2010, 2011, we came up with an iron chromium anode. It was basically chromium 90%. And this is some data you can see on the left side here. This is the pristine sample. This is after several hours at, 1565. And you see it doesn't look beautiful. That's because that's the drag out of the molten oxide. Believe me, if that thing were not stable, it would melt like a popsicle on a hot summer's day. So that was the first demonstration of it. And this was published in Nature. And the reason I'm showing this is that, people think that metallurgy is like caveman chemistry and stuff like that. This was published in Nature. Nature publishes an article about metallurgy maybe once in a decade. But they took this one because they knew this one was of value. So then the next move is we started a company. We started Boston Metal in 2012. This was with Antoine Eleanor, who's now a professor at MIT, and Jim Yurko, who's the head of metals procurement for all of Apple. That's a fruit company in Cupertino. You may have heard of them. Yeah. So we started the company, and it's on the path of upscaling the technology. I told you, it's a 20-year thing. You say, well, where's the steel? Well, it's only been 12 years, which is nothing in tough tech. So design, construct, operate, self-heating cell at scale, and so on. And then to fabricate the inert anode. When we worked at MIT, we were using anodes about the size of a pencil. That's easy. But now we have to make things the size of coffins. And This is chromium. Chromium is brittle. You can't cast these things. You do powder metallurgy, all this stuff. So we're on the journey for that. And ultimately design, build, operate the multi-anode cell for months at a time, and make metal to specification. So that's why you don't see innovation in metals. The demand is so high and the price point is so low. This is the hardest problem you could have. I mean, if they were making titanium, okay. If they were making neodymium, oh, good price point. But steel? What's the price point of steel? It's like $500 a ton. $500 a ton, that would be like 50 cents a kilogram. Go to the supermarket tonight and show me anything in the supermarket that sells for 50 cents a kilogram. That's the selling price of steel. That's the challenge you have. Here's 2014, and in 2014, we'd already designed and built the very first self-heating cell. So you can see in the background, this thing has a single current. It's, I don't know, this is probably about 7,000 amperes. And across here, inside that box, is a cell that's circular symmetry with a central anode. And it's drawing some thousands of amperes and without external heaters. And we're making liquid iron in there, and it's coming out at white heat. You're going to see they're going to break this thing open and tap it. In aluminum smelting, they don't even tap from the bottom. They're afraid to do it. They siphon from the top. So this is coming out. They're going to pour it into this transfer ladle, and then those things in front here, they actually have the Boston Metal logo on them, and they'll eventually pour it into there and so on. That was back in 2014. So, I mean, this is really making rapid progress at some level. So what do you see? You see better metal with zero emissions at parity pricing. I do not accept the notion of green premium. Green premium is lame. It's an excuse for a failed technology. You should not be paying more for something green. It's a chance to hit the reset button. You should be paying parity or less. And so our goal is to make the metal at the competitive price point to legacy technology and unsubsidized. Again, you're relying on government subsidy to get to your price point. Lame, you failed. Lame, you understand? No exceptions. All right. So if you put all those together, you have disruption. And this is the face of disruption. This is one of our steel workers. This is Amanda. She wants to bake steel. That's the new steel worker. All right, so let's go to the next one now, moving along. So I think we want sustainable electricity if we're going to achieve a sustainable modernity. By the way, when you look at this image, where you see light, you see the modern world. Where you don't see light, there's one of two conditions. Either nobody lives there, or the place hasn't been electrified. And if people live there and it hasn't been electrified, what's the number one priority? Electrify the place. That's what gives people a chance to participate in the modern world. Without electricity, you're cut off from the modern world. By the way, you know this is a collage. I show this to some audiences and they think this is the world at night. No, you know, when it's dark here, it's light over here. The world never looks like this. If it ever does, it's a really bad day for all of us. Yeah. So what's the key enabler? The key enabler, because I know people here are working on photovoltaics and so on and so forth. So we have them. So why don't we have widespread deployment of renewable energy and retirement of the hydrocarbons? It's because we can't treat the intermittency. We need massive stationary storage. Otherwise, nobody wants electricity that only works part-time. And when I started this project, I realized that the number one problem with stationary storage is the cost. The price point is too high. Can you imagine if you could generate electricity, say at 5 cents a kilowatt hour, photovoltaics, but you've got stationary storage, and so you take some of the electricity in the middle of the day, you use it for your powering your appliances and devices, and some of it you bank. And then after sunset, you draw from the storage device. And the cost of electricity, by the time it leaves the storage device, after you account for the capital cost of the storage device, the operating costs, the inefficiency, there's going to be second law of thermodynamics, blah, 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 blah. Now the electricity costs 25 cents a kilowatt hour. You say, this is nuts. I'm not doing this. So the price is the main obstacle. So that should be the number one priority. So I said we had to change the paradigm. The paradigm for research in the university is invent the coolest chemistry, publish in the top tier journals, and you spin out the company, and that's their problem, to chase down the cost curve. And they will. They will. But not here, because it's not battery versus battery. It's battery versus hydrocarbons, and hydrocarbons are fantastic. They're abundant, they're cheap, they're efficient, and so on. So how are you going to match that with some discovery that was really cool? It's not going to work. You have to think about cost. That's why I called it cost-informed discovery at the discovery stage, not when you flip out the company. When you're in the early stage, you have to be thinking already about the price point. So when I think about storage, I say confine the chemistry to earth-abundant elements. Yeah? I said in the TED Talk, you want to make something dirt cheap? Make it out of dirt. And preferably, I didn't realize what I was saying at the time. I said preferably local dirt. We didn't worry about supply chains back in 2012. We thought globalization was great, you know, everybody's one big happy world and so on. We know that's wrong, right? Now, you better have something local. If you can't see from here to the mine face, you're in trouble. So think about local sourcing. And think about easy to manufacture. Why do they call it a gigafactory when they build a lithium-ion battery plant? Because it costs $5 giga to build the plant. Because it's so expensive to make this stuff, right? So already conceptualize a battery that's going to be easy to manufacture. You have to think about all these things, not just cool chemistry. That's not enough. So I also said pose the right question. You see when I posed the question, I said invent a colossal cheap storage device. I didn't use the word battery. Because if I say the word battery, that immediately conjures up an image of a right circular cylinder. And I don't know what the shape is going to look like. I just want it to hold charge and give it back on demand. And by the way, don't go to the experts. If you go to battery experts to invent a battery, they'll just talk you down and say, oh, you're stupid, this is crazy, we already tried everything that can be invented has been invented, stuff like that. So don't go to them. So I looked, because it's about economics, so I looked at the, what's adjacent to battery electrochemistry? It's electrometallurgy. So look at an aluminum smelter. So I'm going to go bilingual now. I'm going to use the UPAC nomenclature, aluminium. Even though I'm from Canada, it's still aluminum in Canada, it's aluminum in the United States. By the way, the Charles Martin Hall patent of the aluminium process, it's aluminium. They changed the name to aluminum somewhere in the 1890s. I don't know why, but in Europe, they kept aluminium. And now International Union of Pure and Applied Chemistry says it will be aluminium. Did you hear that? It's aluminium. So let's look at an aluminium smelter. This one is Elliott in Canada on the north shore of the St. Lawrence River. And this is probably 4 volts, 500,000 amps. This is about 2 gigawatts continuous. That's about 30 meters left to right, probably going back about 1 kilometer. And this runs 24/7 at about 2 gigawatts consumption of electricity, and yet it converts dirt into metal for about 50 cents a pound. And I said, this is a modern miracle. And I said, if I could just take that thing and teach it how to store charge, not to drink electricity, but to store charge and give it back on demand, I know at the end of the day I'm going to have something that's big and cheap. So I'm trying to take something that's big and cheap and traffics in electrons and teach it to be an energy storage device. Everybody else is trying to take something like this and teach it how to be the size of this room. We'll see who gets there first. But believe me, putting a gazillion lithium-ion batteries to make that thing, I think that's I wouldn't spend my time doing that. So here's the invention. I call it invasive electrochemistry. So what I did was I took everything I knew about electrometallurgy and I crossed it with battery chemistry. So somebody came to see me and said, hey, you learn all this stuff about electrometallurgy. Do you think that's useful in batteries? And he left my office. And I thought about it. I said, well, what if we had liquid metal electrodes and stuff like that? So there's the liquid metal battery. So it's all liquid. Like normally people think of batteries as solid electrodes, liquid electrolyte. And I said, well, what if we made everything liquid? Because that's how we run an aluminum cell. So we have at the top here, this is one embodiment. So we have liquid magnesium on the top. On the bottom, we have liquid antimony. And in between, we have a molten salt. And they lie on top of one another. The liquid metal is insoluble in the molten salt, and the molten salt is insoluble in the liquid metal. So they just lie on top of one another, stratified by density. And there's no need for membranes, separators, or anything. And of course, you've got to heat it up to get it to the temperature. And then when you discharge it, magnesium wants to alloy with antimony. I just told you magnesium is insoluble in the electrolyte, but magnesium is smart. Magnesium knows that if magnesium becomes magnesium ion, then the magnesium can go through the molten salt. And those excess electrons, they go through the external circuit and power the devices. And then when the magnesium gets to the other side, it sees the antimony, it acquires the 2 electrons and then alloys with the antimony. So over time, the top layer gets thinner and the bottom layer gets deeper. Then that's how the battery discharges. And as it discharges, the current passes and generates heat. And we trap that heat. In a lithium-ion battery, that's a threat. In this case, it's good. And then to charge the battery, we force current through it, and we're essentially running an electrorefinery. And by passing current through here, the magnesium leaves the antimony, goes across the electrolyte, goes back to the top, pure. So we've purified the magnesium, we've purified the electrolyte, and we're purifying the antimony. And we're generating heat. So every day, you're going to discharge, generate heat, trap it. Every day, you're going to charge it in the middle of the day, generate heat, trap it. And that's how the thing runs. There it is. So I showed you magnesium antimony, but, I'm a teacher, so I said, well, what else can we do? Well, over here, all the most electropositive elements, they could be the negative electrode, the one that's on the top. So we've in fact built magnesium, we built lithium, we've looked at calcium. All of these could be candidate electrodes, which means this thing can be customized depending on your location. Some places it makes sense to use calcium, some places it makes sense to use magnesium. And same thing on the other side. So you want to go to the electronegative. So you want to put a really good metal. These ones over on the left side, these are the most electropositive elements. They're the best electron donors. So you take a good electron donor and you pair it with a good electron acceptor, but not with a non-metal, because the non-metal is an insulator. You see what I'm thinking? So once you figure out what the things are, the limitations are, then you come up with these things. And there was a paper in Nature on this one as well. And tenure means never having to say you're sorry. So I don't need to publish, but I do publish to launch the careers of the young people who work with me. And the people that are co-authors on this thing, all their careers were launched because they got published in Nature. Especially there's a couple of people here, actually, they're a couple, married, and they both went back to China, red carpet treatment for them because of this. So people respect this. And the thing for us is it meant that batteries, which they thought was, caveman chemistry, it's nature worthy. And all of a sudden other people say, oh, I'd like to work on batteries now. Now, before you didn't, because you thought this was, I don't want to be associated with either. I don't want to be associated with that stuff. Yeah. So it was startup time. This came before Boston Metal. I didn't want to be involved in the startup. And my students came to me and said, look, you talk about science and service of society. Well, how do you think the battery is going to get in the hands of society? You got to start a company and get it out there. So they persuaded me. I said, okay, all right. I didn't want to be involved in startup and money and all that stuff. So all the sexy names were taken, so we named the company the Liquid Metal Battery Corporation. Can you think of a worse name? That's what it was. And then we changed the name to Ambry. And how do we get Ambry? I'd heard that, you know the company Cisco Systems, they make routers and all of that stuff. Somebody told me they named it Cisco Systems because it was founded in San Francisco. And I said, So I took Cambridge and I kept playing with the word Cambridge, and Ambry popped out, and Ambry.com was still available as a domain name. So I said, that's an omen. That's your name. So we named the company, we rebranded it as Ambry. Now, I got my first funding from Bill Gates. Now, I'm Canadian. I'm very polite. I didn't bother Bill Gates. Bill came to me because he had been watching my chemistry lectures, which were now already being hosted by MIT OpenCourseWare. He was watching them every year, like 35 lectures. This guy was really chowing down Gen Chem. He really wanted to understand this stuff. So it was August of 2009, and I got a note. He just stepped down as the CEO of Microsoft. And I got an email from a woman who represented herself as his executive assistant. And she says, Mr. Gates is coming to town on September 25th. He'd like to meet with you. Would you have 90 minutes? I disregarded the email. I thought the students had hacked into my account. I said, I'm smarter than that. You're not going to play with me. So I ignored it. And she wrote again about 10 days later and said, maybe you didn't see the email, but Mr. Gates really wants to meet with you. So I showed the email to some colleagues, and they said, I think this is real. I think she would probably respond. So I said to her, all right, would you mind telling me what this is about? Then he jumps in, like 4 paragraphs of, this is what I want to do, this, very prepared and so on. And so anyway, long story short, he came. It was a Friday. I just taught this freshman chemistry class and sat with him for 90 minutes. We talked about computers, distance learning. This is way before Zoom and all that stuff. And towards the end, he says, so what are you working on? And I sketched the idea of the liquid metal battery on a whiteboard. We had no data yet or anything like that. He looked at it and he says, 2 things. He says, seems to me that the basic premise for a battery for stationary storage should be different from the premise for mobile storage. I said, you're smart. I have colleagues here who are trying to figure out how to make lithium-ion batteries work for stationary storage. The second thing he says, if you ever think about spinning this out, let me know. I'd be willing to put some money into it. And so a year later, 2 of my associates, a postdoc and student, went to meet with Bill, and he became our first investor. So I met Bill Gates, not because I wrote a dynamite opinion piece for the Wall Street Journal. I met Bill Gates because I was dutifully teaching a big freshman chemistry class. You know, so all of the people that are shirking their teaching and so on, they should hear this story, because you don't meet anybody by not teaching. Oh, that's quiet. It's very quiet. I like that. And the big French energy giant Total was now engaging with MIT, and they had sponsored some of my initial research. And when they heard that we were starting a company and Bill was involved, then Total matched Bill, and that's how we got started. So it's been a long journey, and it's not like everything's beautiful, everything comes our way. It's been really frustrating. There've been a lot of setbacks, disappointments. It's 15 years old. You cannot call yourself a 15-year-old startup. That's like saying, I have a 15-year-old child. You do, yeah, technically it's a child, but it's not an infant anymore. So, but Microsoft has signed on to be the first customer for their big servers. We know that computerizing the modern world is going to ask for gigantic amounts of electricity. You know, so you think you send an email, no paper, it's so cool. You don't understand what the CO2 emissions are from sending the email. And it's going to cost us big. The copper that we're going to need, it's big. We don't have the capacity in the grid. If you try to shove more current down those wires, you'll melt the insulation, and then you'll melt the copper. So You're going to lay more copper wire. Well, I'll just go to copper.com and just have the Amazon truck deliver it by tomorrow. No, you're not. XL Energy, and this is a South African company, Earth and Wire. So they've all signed up to be customers. And the manufacturing facilities are just outside of Boston and Marlborough. But we've gone through one bankruptcy, because the market doesn't have the appetite to fund pre-revenue companies. So everybody says we're 100% behind sustainability or decarbonization and so on, but not with the money. Follow the money. The money's not going into pre-revenue, and everybody's just sitting on the sidelines. We didn't take government money. Never wanted, on principle. I always felt that government money into a startup is wrong because I'm asking my neighbors to pay for my company. Government money at the university for exploratory research, yes, but not the other. So what's happening right now is that China has overbuilt capacity, and instead of trimming back on productivity, they're just cranking the stuff out. There's some LFP, the lithium iron phosphate variant of lithium ion batteries, this is being priced at $37 a kilowatt hour. I mean, this is crashing the market. What's going to happen? All these battery startups are going to fold, and then we just have to sit and wait. But, I don't care what people do in portable, although I think driving a car with a lithium-ion battery, as Clint Eastwood says, the question you got to ask yourself is, do you feel lucky? Because it's just a matter of time before there's only two kinds of lithium-ion batteries, those that have caught fire and those that will catch fire. But people, when they put lithium-ion batteries into massive stationary storage, this is criminal. This is the Moss Landing, and this is a 3 gigawatt hour storage facility with lithium-ion batteries. And I thought that they were using LFP. They used NMC. NMC is the most, the one that's most likely to catch fire. And that's what it was. So this is what the Moss Landing fire was, and the fumes from this. They closed the Pacific Coast Highway on the previous fire, not because of the flames, because of the fumes. Those fumes are so toxic. But this, what it gave was nickel oxide, manganese oxide, cobalt oxide, and this is right next to the salad bowl. So there's the strawberry fields, the lettuce, and all that soil has got a shower of those oxides. So when you go to the supermarket, you see Driscoll's strawberries. Of course, you got to ask yourself, do you feel like it's time for some transition metal oxide? So that's the image from the fire. Oh, did I mention? That's the fourth fire they've had there. And this is Vistra from Dallas. I mean, these guys should be fitted for orange fabric, This is unbelievable. I don't know who's worse, the people that did this or the people that permitted this, but this is crazy. And by the way, this is beautiful wetlands. I used to have a house not far from here. Just Moss Landing is north of Monterey, and I was on Monterey Bay. I'd drive past there, and it was beautiful wetlands. So now they took down a gas-fired power plant, covered the place with solar panels, then put this thing in. But it's green. We have to be better than this. Okay, so that's the two vignettes, but I thought, well, maybe there's time for a bonus round. Yeah, I think you can squeeze this in. So I wanted to tell you what I'm doing now, as was mentioned in the introduction. So I'm a professor emeritus. I left MIT in 2022. June 30th at midnight, I left. So I'm formally retired. That's why they say emeritus. That's that's Latin for extinct volcano. But I decided I wanted to do something else. So I started my own skunk works. It was a labs. And it's for R&E, research and education. And so we want to have free reign to do anything we want. No proposals. If somebody says Washington, D.C. to me, I go, I've heard of the place. I don't do any business with it. So this is where you imagine the unimaginable. And then do rapid testing in the laboratory. Well, who's going to fund this? Because the first question is, how do you monetize this? Because it's a foundation, so it's forbidden to be profit-making. But we spin out companies, we'll figure it out. And I got funding from Schmidt Futures. Eric Schmidt was the CEO of Google. And he and his wife set up a foundation. They fund a lot of things in life sciences, women's health, even microloans for people in developing countries, all kinds of laudable stuff. And I approached his chief executive officer, and I said, I don't see anything at the website about climate change. Is Eric interested in any of that? He says, why don't you pitch something? So I pitched this idea, and he decided to give us some anchor funding. So we started with the funding from Eric Schmidt. I say funding the unfundable. And so originally I said it was for climate change mitigation, but in the present climate, we don't talk about climate change mitigation. We talk about national security. We talk about supply chain firming and all that stuff. They end up with the same solution, but just how you label it. And so the products are companies, that's the R. And the E is the new inventors. So we're inventing inventors, we're training trainers, we're teaching teachers. And that's the thing that happens here. Because people come here and after they get the Sadoway treatment, they're changed. And it's different from the treatment that they get as postdocs in a university. So what was my pitch? I said it was extreme electrochemistry. That's what I'm doing. I'm not doing everything. I work only with extreme electrochemistry. So that's non-aqueous electrochemistry. I know some people are interested in aqueous, full battery, stuff like that. I don't touch that stuff. Aqueous, no. So either molten salts, and that's high temperatures, body temperature up to 2,000. You know that first reactor that we built, the self-heating reactor, we ran that thing at temperatures above 1,900 degrees Celsius. No problem. I know we could easily go to 2,000. With 2,000, you could be doing electrolysis in molten alumina. I mean, it's so cool, the stuff that you can do. And then molecular liquids. This is a class of liquids that people don't do much in. I'm looking at things like thionyl chloride, liquid ammonia, go down, 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 down. All kinds of interesting chemistry there. So with those two extremes. So we're looking at 21st century solutions. One is in metals recovery, both in primary extraction, recycling, without emissions to air, to water, to soil. So we're looking at rare earth metals, scandium, gallium, germanium, all this stuff. And of course, this is related to national security. And just as I showed you with steel, it should be better metal, cheaper than that produced by the legacy processes. And then the second area is CO2 zapper. I said at the beginning that we were talking about low carbon. I didn't say no carbon. I said low because we're going to be burning hydrocarbons. But if you want to burn hydrocarbons, those CO2 emissions, well, get rid of the CO2 emissions. Everybody else says get rid of the burning of the hydrocarbons. No, that's a simpleton's answer. So I call this immaculate combustion. I kind of like the name. Some people think it's a little bit too edgy, maybe it's like religiously insulting and so on. No, it's not. No, it's not. Stop that. Stop that. I refuse to be canceled. All right. So what this means is that you can burn carbon without CO2 emissions because we're going to destroy the CO2 before it leaves the chimney. And by the way, there is no answer. How do you produce cement? I showed you steel was almost 10%. About 8% of world CO2 is from cement. And people have dabbled in these other alternatives, but man, no one's going to build bridges out of that stuff. No one's going to build a skyscraper out of that stuff. The Portland cement has certain standards. They have to be met and the price point. So we can get rid of all that stuff without CO2 emissions. And this last one is my pet project. Even Eric Schmidt was saying, what's this have to do with climate change mitigation? But I just can't resist inventing other batteries. So I said, well, I call it whole earth battery because it'll operate at temperatures as high as plus 80 Celsius with passive cooling, which you cannot do with lithium ion. and it will operate at minus 80 Celsius, which no battery will operate at because all the electrolytes are frozen. And so what's the secret? The secret is the electrolyte. So I'm using thionyl chloride. Thionyl chloride boils at about 75, plus 75. The freezing point of thionyl chloride, it's on the FM dial. It's minus 104.5. Minus 104 degrees Celsius? That's fantastic. That's a magic liquid. Why does anybody do anything with it? No imagination. Or the funders won't fund it. You try to pitch that, a rechargeable thionyl chloride battery, people are going to say, well, thionyl chloride will be attacked by this, that, and the other thing. But you know what's killing innovation? It's the assessment requirement that includes likelihood of success. Well, if you want radical innovation, and you're going to measure radical innovation by not the value of the idea, but the likelihood of success, there's a chance it'll fail. But what if it succeeds? You know, like most people are afraid of success, I think. I don't know what's the matter with them. No? So that's why you don't see innovation. I say, I don't care. No. I said, tenure means never having to say you're sorry. Retirement means you can say anything you want. You can't fire me. I already quit. Sorry. So, and just the last piece here, let's be reminded that the battery was discovered by a professor. Oops. How did that happen?
Stop me.
Oh.
The code that came before. He just spoke about the code.
Oh yeah, the coders. Wait a minute, I'm going to fix this. I'm undaunted. This is called grace under pressure. You see, I don't. Okay, keynote. Now open recent, Sadoway Rice. Let's go to there. Push this. All right, let's get down to the end. You don't want to see those slides again. And we get to the end. This is. I'm just standing between you and the reception, so that's not important. All right, and then we push this one, and then we push this one. You see, very graceful. No stress, no, just, when you see grace under pressure, you go, how does he do that? Well, he's retired, he doesn't care. All right, so this is Volta. Volta discovered the battery in the University of Padua in the 1790s, and he was a professor at a university. So with the discovery of the battery, he demonstrated not only that we have this for the first time energy storage, but he demonstrated the utility of a professor. Before Volta, nobody imagined a professor could be of any use, but Volta showed that the professor, given the resources and left alone and not meddlesome by administrators and government agencies, it would be amazing what he can do. So here's the first battery. It's a stack of coins, zinc, silver, separated by cardboard soaked in brine. Now people look at this and they say, he gave us the battery. That's true, but he gave us something else. For the first time, we had electrons in motion, right? It's a primary battery because the dynamo hadn't been invented yet. So why would you have a rechargeable battery? Because you don't have any source of electricity other than to bleed another battery. So that'd be kind of stupid. So this, for the first time, is electrons in motion. And within 10 years in northern Italy, people took this invention and they were using it for practical purposes. They were using it to electroplate metals. And there was no venture mentoring. There was no entrepreneurship group. There was no venture capital community. They just did it because they were resourceful. But you understand that with this, for the first time, we have electrons in motion. Prior to this, the word electricity was already in the English language. It goes back to about 1646. And it was used for static electricity. So if you took a piece of straw and you put it in a cup of water and it's sitting floating on the top of the cup of water, and you take a piece of amber and you rub it with wool and you build up static charge on it, and then you can hold the amber above the straw and move the straw, which, by the way, in 1646 was sorcery. The notion, because it was a Newtonian world, the idea that you could exert a force on something without direct contact, this was witchcraft. I mean, how do you do that? They didn't understand any of this. But that was the extent of electricity. It was, moving, you can put a smile on a child's face, but that's all. You couldn't do anything with it. But with this, for the first time, you can do things. There's technology here. And with this, there were physicists. What did the physicists do? They looked at this and they said, wow, we noticed that when current runs through a conductor, it generates a magnetic field. And then somebody had the audacity to say, well, if a moving electric field generates a magnetic effect, would a moving magnetic field generate electric current? And guess what? It does. And that was the birth of the dynamo. And everything we have in the modern world starts with this. This man doesn't get the credit for this at all. It's not because people are being nasty. I don't think people have figured this out. Maybe I should write something for, like an op-ed piece for XYZ. Nobody's reading newspapers anymore, so I don't know what that means. But you understand, this is here because without this doesn't exist. You think just without this, somebody's just going to say one day, hey, I think let's just move some magnets around and see if I can generate electricity, which I don't know what it is, because I've never seen electrons in motion, so I don't know what it is. These are the steps. I was in Padua for a conference in September and went to the university. I mean, it's a fantastic place, They had university there in 1500 and so on. That's where Da Vinci, you meet Da Vinci and say, you look at all of his beautiful, you look at the sculpture of David and say, yeah, but where did he get his degree from? I mean, after all, did he go to Harvard? No, he didn't. Ask us questions, All right, so I've just, inventive process, just to sum up, ask the right question, all right? Look outside the field for inspiration. Don't hire experts, hire the anti-experts. All the students that I had were not experts. And many of them didn't know electrochemistry until they met me. They didn't know liquid metals, molten salts. But they're young, hungry, idealistic, unjaded. They don't know what can't happen. So I just say to them, oh no, you can make this work. It's called confidence building. That's called mentoring. And I want people asking me today at lunch, what do you look for in a student? Well, you sense, are they curious? Are they willing to accept defeat, keep going, and empower everyone? I don't rule by fear. I rule by, here, I set up the problem. I gave you the orientation. Now come on and back in and tell me something I don't know. And of course, you encourage independent thought. I was once in a meeting with Bill Gates, and there was a bunch of guys sitting around, and he said something. One of the guys at the end of the table says, no, that's not true. I thought, okay, we're going to see something here. Bill says, really, I don't understand. What do you mean? The guy explains, and Bill says, yeah, I got it. I see your point. See, so what's that modeling? It's modeling that we're free to disagree with each other. We're not saying that you as a human being are worthless. We're saying what you just said I think is wrong. It doesn't mean that you are being offended. If you take personal offense at somebody who criticizes your idea, then there's something else happening. Right? So that's important. All right, so I think most industrial chemistry will become industrial electric. Anything that can be electrified will be electrified if we go to a dominantly electric economy. So there's a bright future right now in electrochemistry. Obviously, you can see I kind of like electrochemistry just a little bit. And so electrometallurgy, metallurgy in the future is not going to be chemical. It's going to be electrochemical, because you just don't want to have CO2 emissions. If you're going to electrolyze chloride, you're going to make chlorine with a carbonyl anode, which means you're going to be generating dioxins, all this stuff. this is all under scrutiny. So I hope I've shown you that there is a path forward for science in service of society and profitable sustainability. I don't want us to be green and poor. I want us to be profitable, sustainable, and spread the wealth more uniformly around. So let's get started.
The floor is open for questions. There's microphones, so just please wait for the microphone to come your ways. Maybe Jackie, you can kick this off. Yeah.
Incredible presentation. So I have a basic scientific question, so it's a curiosity for me. So how are you managing the temperature effects in this lithium batteries, thermal expansion, or I don't know?
Yeah, so as I said, the battery is designed to be used. It's not designed to be sitting as a UPS, uninterruptible power source. So if they're daily used, we've calculated the joule heat that would be generated on discharge or on charge. And that heat gives you a thermal front, and you trap it with the insulation. And by charge and discharge on a daily cycle, you generate enough heat to keep the thing from freezing. And by the way, just to be clear, it can start to freeze because it doesn't freeze instantly. It freezes from the outside in, and it can freeze a good deal away. And then when you start passing current to charge, you'll melt back and so on. So there's some elasticity. And to your point about the expansion and so on, because they're always being liquids, it's not as though you have a freezing and well, water is the exception. When water freezes, it expands, but we don't have that. The metals would actually contract. But yes. Yeah. So that's under consideration.
Just to pick up on this, you're applying huge magnetic fields, like huge currents.
Currents.
You must be getting huge magnetic fields, right? Associated. So how do you, since you spoke about?
Yeah. So this in the installations that we have so far, it has not become an issue. But the very first time I visited an aluminum smelter, it was in Muscle Shoals, Alabama, Reynolds Aluminum, and they were rather small cells by today's standards, about 150,000 amperes. And we pulled up in a car, and the guy from the company says, "Okay, give me your watch, give me your wallet. Everything stays. We'll lock it up in the glove box. When you go in there, you don't bring anything. You go in there with your watch, and you go in there. The magnetic fields from those things, the hands are going to be spinning like this, and your credit cards will be demagnetized. So the magnetic fields are really, really high. So in the aluminum smelter, they have two pot lines, and they have the current balanced on the two sides. And in the aluminum cell, it's about 1 foot deep of liquid aluminum. And what happens is it's a DC current, but the anode is smaller in area from the cathode because you have to have room to let the gas escape. So it's a divergent current. So because it's divergent, you have a magnetic force on the bottom, J cross B, and now on the bottom it's doing this. And you actually have a surf on the liquid aluminum. So you have to keep the anode cathode spacing high enough so that it doesn't splash up and short, because if it shorts, it'll blow the substation and stuff like that. It's really cool. It's cool chemistry, cool physics, but you just better be mindful of it.
Yeah.
Great talk. So I was curious about the first part, the direct metal oxide reduction to metal. But for steel, you still need carbon. So do you add the carbon layer into the?
Oh yes, yeah. So so when we make liquid metal from iron oxide, it will be pure iron, and so then we will add the carbon to to raise up, because in the conventional process today, they have unacceptably high carbon levels, and now they have to remove the carbon. First they removed the oxygen, now they have to remove the carbon. So we just go from oxide to pure iron, and then we carbon. You could blow methane through it. There's various ways of getting it up, because it's down around 1% or something like that. Unless you're making cast iron, then it's 4 or 5%. Yeah.
Your title was decarbonization and profitable sustainability. So for that 15 years, he's topped these startups where you gain the gigaton scale, believe
Correct.
there's a
Correct.
profitability. I know philosophically you don't want green premiums or government funding, but
All true.
transformative would it be if there was the green premium, if there was the carbon tax, if there was a mandate, the steel, the trees, other materials need to be made before materials, could that enable this to scale up?
It could. It could. I was at a workshop where people were looking at exactly this question. And they said, well, if we just let markets take their course, it could make it longer than 20 years. So you raise a valid question. And so people were still squeamish about calling for carbon taxes and subsidies and so on. But they said there may be another policy lever, and they called it procurements. So they could say that we're not going to tell you how to make your steel, but the steel that's going into this bridge or whatever the federal project is, it must have a carbon footprint of no higher than this, where this is lower than can be attained by conventional technology, and then that would start to force people to make the necessary changes. Otherwise, they would lose or they wouldn't be eligible for the contracts. But you know, you raise a valid question, and I mean, if we want to move things along, maybe we have to give them a nudge. So I wouldn't be opposed to seeing some policy levers being used. I just want to resist the temptation of saying, in my business plan right from day one, I'm counting on so many dollars a ton subsidy, blah, blah, blah. I think that's, this is what happened in Europe with the SSAB and the hydrogen plant and so on. They're relying on subsidies, and eventually people are going to say, I was at a conference where people were talking, there was a fellow from Germany who was saying, you know, people are so gung-ho on this, they would be willing to pay premium. I think he was using numbers like 30%. And I was on the stage, there was a panel, and he was talking, and I could see all the heads shaking, and everybody saying, no, no. And no one's going to pay a premium. So let's say you're an automobile producer. You're not going to pay a premium of 30% on the steel just to be able to say this car was built with only green steel. So you've raised a really good point. I mean, how do we get out of this conundrum besides just waiting and hoping that market forces will choose the best path forward? But I don't have the answer. I have the humility to say, I don't know what the right answer is.
Questions with the back there, and then come back to you. Okay, he has a microphone. Yeah, go for it. Ocean, go.
Sadoway, very good talk. I have one quick question regarding your both metals, this molten salt electrochemical iron reduction. So you mentioned that the one challenge is the anode side because it's very harsh reaction environment. Is it the potential, the positive potential that drive the harsh degradation of the anode, or is the high temperature that these anode cannot sustain a long time? And another question is, how do you think you can leverage some existing materials of industry that could fabricate similar harsh material that can be leveraged for large-scale deployment?
Yeah, so first question, it's everything, because if you want to electropolish a piece of metal, you make it the anode, and that way you're actually trying to dissolve away the surface and stuff like that. But we need an anode because we have to have the oxidation reaction to balance what's going on at the cathode. So right now we're using carbon, and then the carbon reacts with the oxygen that comes from the iron oxide and then makes CO2. So we want to get rid of that. And the high temperature is definitely a factor, but the design of the anode with the chromium 90% iron, 10%. It forms a surface film of an iron chromate, and that surface film is protective, and yet it allows current to flow. And yet there's still, the molten oxide is voracious. It will dissolve oxides, and the chromate is an oxide. So, but when you're running hard and you're generating oxygen, the oxygen, oddly enough, is actually protective on that. So it's figuring out what the operating window is for it. And I don't care if it eventually dissolves, as long as maybe it now has become an oxygen evolving anode. And the rate of replacement of that anode is economically acceptable. And so you get oxygen evolution, no CO2, and the metal that's produced. If you're asking for mild steel for a rebar and it has some chromium impurity in it, you'll say, it's fine with me. It's not going to make it worse. Next, you're paying for a premium. You could turn around and charge people a premium because it's got some chromium impurity in it.
We'll go there, and I think there's a question there. So that Andrew is on that.
Thank you for your talk. I just had a question about the parity pricing and
Yeah.
trying to do that without having to add subsidies and things like that.
Mm-hmm.
So for your technologies, are you able to meet parity pricing or close to it straight out of the lab, or are you kind of betting on the scaling law that eventually you get there? There's really like cement, steel are very hard to beat industries. They have 100 years of experience, probably that costs down. So how do you approach that or choose technologies to focus on?
Well, it's by the judicious choice of the chemistry, so that you're, I wouldn't say betting. I mean, I think we chose them because we expected that the capital cost of the reactor is much cheaper than the capital cost of the blast furnace, plus the coke ovens, plus the pelletizing plant, plus the basic oxygen furnace. If you take that out of the equation, now you've got some cushion, all right? And then the energy consumption is actually lower because the blast furnace is radiant heat. A lot of the heat is unnecessarily being generated and going in the wrong direction, whereas in electrolysis, the current is running between the electrodes exactly where you want it. So it's hottest in the center of the cell and cooler on the periphery. So there's reasons to expect that this thing can achieve acceptable numbers. Plus we have the aluminum industry, which itself is over 125 years old, and they take dirt to metal for less than 50 cents a pound. So we're confident that it can be achieved.
Question here? Yeah.
Hello, Professor. Your talk is really great. And my question is about, so you know that there are also approaches to decarbonization in the steel industry, such as utilizing hydrogen in the steel making process.
Yeah.
So do you think of your technology involves metal compared to utilizing hydrogen as like, what are the biggest pros and cons?
So hydrogen does work. However, hydrogen is let's look at SSAB, which is in Sweden. They have magnetite there, which is very high purity iron ore, but it still requires a front end. And that means that if you have impurities such as silica and other elements, but silicon is the primary one, because most of these iron oxides are silicates. So hydrogen will reduce silica to silicon. And so you will not make pure iron, you will make ferrosilicon. And the way you get around that is you have what they call a front end. So you start with the ore, and then it's typically dissolve the ore into some acid or maybe an alkaline solution, and then you precipitate out the undesirables, and then you're left with the high purity iron oxide and so on. That's point number one. Point number two is that the reactor in which the hydrogen reduction takes place, it's a shaft, and it runs as a countercurrent reactor. So you feed in iron oxide at the top, you feed in hydrogen at the bottom, just the way they do today with natural gas. It's called DRI, direct reduced iron. But you realize that you don't throw chunks in, and you don't throw fines in. You have to make pellets. of a certain size, a certain porosity. So now you got the capital cost of the pelletizing plant, which we don't have. We can take ore and just throw it in. So we don't have a purification step. We don't have a pelletizing step. Now this runs at about 900 degrees Celsius. And when you're done, you have little pellets of pure iron, just as you have in DRI, right? But the downstream operations in steel making need liquid metal. So now you take all of these, you harvest them up, you put them into an electric arc furnace. An electric arc furnace has to melt all this stuff, and an electric arc furnace runs with carbon electrodes. So there's some CO2 emissions from that. And when you add up all of these incidentals, capital costs, operating costs, and the price point of hydrogen, you know, people are talking about $1 per kilogram. I mean, I don't see any evidence of that. We know what the binding energy is between hydrogen and oxygen. You know, there's 100 years of catalysis research and so on. I mean, you still have the IR drop between the electrodes. And so you have to get really, really cheap hydrogen, and you have to have really, really purified iron oxide. By the way, in aluminum cells, they start with bauxite. Bauxite. It's a mineral, and it has aluminum oxide, has silicon oxide, iron oxide. Those are the two major ones. There's a whole bunch of other tramp elements, okay? And so first thing they do is they take bauxite and they dissolve it in stuff like super, super high pH, like caustic, like pH 11 kind of stuff. Dissolve it and then precipitate out the iron, the silicon, and then capture the high purity aluminum oxide, because the electrolytic cell does only one thing: it breaks bonds. And the same thing in the hydrogen reactor. It does only one thing: it captures oxygen. So if you want high purity iron coming out, you have to feed in high purity iron oxide. If you want high purity aluminum metal, you have to put in high purity aluminum oxide, because aluminum is so reactive, so cathodic. Every other tramp element will be co-reduced and deposit with the aluminum. And so now what? So when you factor in all these things, the polite thing to say is that in certain locations, hydrogen may make sense, hydrogen reduction to produce iron, but I don't see it as a wholesale response to decarbonization. The costs are just not in favor. And you know, as much as you love it, I love when I see people that become hydrogen devotees, they love it so much. And you've showed these economics and so on. And say, I know, but it's early stage. I know it's early stage, but you can't just say, with time, the price will fall. You have to say, by what mechanism? Is there going to be new catalyst? Is there going to be new source? Is there going to be, I don't know what? You're going to run the reactor. Iron melts at 1540. You're going to run the iron, you're going to run this thing at 1600 degrees so you make liquid metal. If you can't answer those questions, you're going to make stuff that's really, really premium priced. I'm sorry. I just tell truth. I don't come to insult.
Maybe a last question, and then we'll head for reception, I think.
Last question. So you mentioned, you put in iron chunks, things like that. One of your slides alluded to cleaning up or dealing with mine tailings, which are a bunch of different crud. So what do you do in that situation?
Okay, so the question is about tailings. Tailings is what's left over in the mining operations. So this is a new thing. New thing, do you hear that? So the classical way that people want to produce high purity metal, as I just said, they take high purity feedstock. So they take oxide and get rid of all the other stuff, so they just have the target metal oxide and then do electrochemistry. With tailings, I'm flipping the paradigm and I'm saying just pass current and electrolyze everything. And so now you're going to make this mongrel alloy that's got, let's say, 3 metals mixed in. Say it's got aluminum, iron, silicon. You go to a second reactor in which you electrochemically refine, and then you separate them. So instead of separating before you go into the primary cell, you electrolyze in the primary cell, and then you refine in the secondary cell. And I can't name names, but we have a project at Sadoway Labs to purify aluminum. We've started with beverage containers. We took a Coke Zero can, cut the skin off it, made that the anode. Because the aluminum for beverage containers is about 95% aluminum and a few percent of iron and some manganese. And some of them have some silicon, what have you. And so we just did this on a hot plate in the glove box, because I had all this experience from the aluminum sulfur battery. We used a chloroaluminate melt at 160 degrees Celsius, just sitting on a hot plate, put in a copper cathode, passed current, made ultra-high purity aluminum in one step. And so you start looking at that saying, well, there's all this stuff out there, you know, because right now to recycle aluminum, you have to go to a smelter that's run by Alcoa. It's not trivial to purify. So that's the idea. The idea is to flip the paradigm of metals extraction.
Well, with that, let's thank Professor Sadoway, and as just a small token of appreciation, I would like to present you this medal, which is for the 50 years of the School of Engineering.
Terrific.
On the behalf of really everybody here in this room.
Oh.
So,
Thank you very much.
thank you so much for accepting our invitation.